Hello classes. Today we're going to do section 8.2, areas in the plane, and if you haven't already, please print the notes from online. The other thing is I have graphed all the equations ahead of time just to save a little time, but you are expected to be able to graph these by hand and not rely on a calculator. So if you're not sure what something looks like, remember you always make a t-table. So for this, just to review how we find area, when we have one curve, we want to find the area between y equals x squared minus 9 and the x-axis from 0 to 6. So we're finding this area and this area. And so if we had a calculator, the easiest way is just to integrate from 0 to 6 of the absolute value. But we have to be able to have a calculator because the only way to do absolute value is in our calculator, or if the absolute value makes shapes that we know, which this one will not. So if we had a calculator, this would give me 54. But let's say we had to do it by hand. Then we have to break it up into two regions. The region that gives you a positive area, which is from 3 to 6, and the region that gives you a negative area, which is from 0 to 3. And what we said is we integrate from the positive area of my function, and then we subtract the integral of the negative integral, because that will give me minus a negative, which gives me a positive. Okay. And then we could integrate this function, and again, if we didn't have a calculator, we would use the fundamental theorem of calculus. So you can pause the video to practice with that, and I'm going to pause it as well to do mine, and then you can check your answer when you're done. So here I showed the fundamental theorem. I integrated each piece, and then I plugged in upper bound minus lower bound, and just be careful with your parentheses and that you follow order of operations, and then you should have got 54. So what's different about today is we're going to be given two curves, and we're going to find the area between those two curves. There'll be two situations. One situation will be in the directions that they give us the domain where we want to integrate from, and then other ones they're just going to say between the two curves, which, like for this example where we have y equals 2 minus x squared and y equals negative x, between the two curves is, if we look at where the two curves intersect, between is this region where my pen is going over. So what we do is we always first draw a graph, if we look through the steps, of the two functions, and then we draw a sample rectangle between the two graphs. So in this case, I want to find the area of the region enclosed by the parabola y equals 2 minus x squared and the line y equals negative x. And if I draw my rectangle, and I can pick anywhere, that would be there between them. Or I could do over here, that would be my rectangle. And so what we're going to do is we're going to find the area of one rectangle, and then if we integrate over my region, the integral, remember, adds all the rectangles together to get the total area of the curve. So they're saying if f of x is greater than g of x, then the height of the rectangle is the change in y, which is f of x minus g of x. So we always want a positive area, so we do the more positive area minus the lower one. So in this case, y equals 2 minus x squared would be my f of x, and y equals negative x would be my g of x. So I would subtract them to get the height of the rectangle between them. The width we can either say is delta x or dx, the change of x, and then because it's a rectangle, we will do length times width. So we will take f of x minus g of x, and we will multiply by the width, which is dx or delta x. And then we integrate over the interval, and if the bounds are not given, we determine where the two curves intersect to find the bounds. So we're going to say in general, like before, a and b are where the two curves intersect, and so then it would be f of x minus g of x, and then we would multiply by dx. So that is my formula to find the area between two curves. So for this, I would integrate f of x minus gx. I guess before I integrate, I should figure out where my bounds are. So we are going to set our curves equal to each other to find the bounds algebraically. If you have a graphing calculator, you can find it with that. But we're going to practice algebraically because a lot of times these are on the non-calculator part. So I'm going to move my x squared over as well as my 2, and I'm going to set it equal to 0. Then I'm going to factor, so I need what multiplies to negative 2 and adds up to negative 1. So that's x minus 2, x plus 1 equals to 0, and then I set each term equal to 0, so I get x equals 2 and x equals negative 1. So those are my bounds. So this is my negative 1, this is my 2. And so then when we integrate, we're going to integrate from negative 1 to 2 of my upper curve minus my lower curve. So my upper curve we said was the 2 minus x squared, so I'm going to do 2 minus x squared, and then I'm going to subtract the negative x dx. And then we're just going to do these in our calculator just to save time. But you, again, if you would like to practice with the fundamental theorem, you can do that. But before you do in your calculator, I would just recommend to simplify because it makes it easier. So I'm just going to change this to plus x. And then I'm going to integrate from negative 1 to 2. And then you can pause the video to practice integrating or to integrate it in your calculator. But you should get 9/2 or 4.5. So that's what we're basically doing, and that's what we're going to practice on all the rest of the slides. So just the key thing is always make sure you do upper curve minus lower curve, and it's if we're going if dx is if we're drawing our rectangles vertically and our width is dx, you want to make sure it's the more positive y value minus the less positive y value. If you switch your curves, you'll get a negative area, so that will give you a hint that you picked the wrong curve to be the upper curve. And just make sure you read the questions very carefully. So for this one, for example, it says find the area of the triangular region in quadrant 1, so that's a key thing, that is bounded by 3 things. Y equals 4 minus x squared, so I graph that here. This is 4 minus x squared. And then y equals 4x minus x squared, which is this curve here. And then the y-axis, which is here. So I'm trying to find actually this region here that I'm outlining. So the region between the two curves and the y-axis. So what's different about this is we don't want where the two curves intersect because we want quadrant 1 and it's bounded by the y-axis. So when we find our bounds, my starting bound is actually going to be 0 because that's the x value that it starts at. My end bound is going to be this one, and that's where the two curves intersect. So I'm going to set them equal to each other to find where they intersect, and then if I add x squared, they add to 0, so I get 4 equals 4x, and x is going to be 1. So I'm going to integrate from 0 to 1. And then I need f of x minus g of x. Well, in this region, that's the only region I'm focusing in, the higher one is 4 minus x squared because the y values are all higher. So I'm going to do 4 minus x squared, and then I'm going to subtract the lower one, which is 4x minus x squared dx. And then I'm just going to integrate it either by hand or using my calculator, depending, like for your homework, if the book says calculator or non-calculator. But again, always simplify first because it makes it easier. So I get 4 minus 4x dx. And then I'm going to integrate this on my calculator. And for this one, I should get 2. Okay, and that's the area of this region here. Okay, so for a third example, it says determine the area of the region between sine of x. So the curve that I'm tracing right now is sine of x. And then cosine x, and you should, again, you graphed cosine and sine last year, so you should know how to graph those by hand without using a calculator. And then pi over 2, x equals pi over 2, so x equals is a horizontal line, and pi over 2 is when cosine is 0, and sine is 1. So it's that point. So the difference here, and then the y-axis, I forgot that. So we want that. So we want this region and this region. And so the difference is the upper curve and the lower curve change in these bounds, which means I need to do two separate integrals. So I'm going to do, if I would draw my rectangles here, the cosine x is higher. But if I draw my rectangle here, the sine of x is higher. Sorry, I said that backwards. So sine of x is this one, cosine of x is the first one, and then sine is the other one. So from from this point where they intersect to pi over 2, we have this curve on top, and then the other one, that curve. So we have to split this into two integrals. That's kind of the key thing. And I think I labeled my graph wrong, just so you know. So this one, is y equals cosine x, and then this one down here is y equals sine x, just to fix that. So what we're going to integrate is we're going to do two separate integrals. So our first integral is going to be from 0 to the point they intersect. So we have to know where sine of x is equal to cosine x. And it's kind of one that you just have to think about if you don't have a calculator. But we know that they have the same coordinate of square root of 2 over 2, square root of 2 over 2, and that's at pi over 4. So we're going to go from 0 to pi over 4. And then we're going to do the upper curve, which is this one, which is cosine x, minus the lower curve, which is sine x. Okay. And then we're going to add, so we're doing two separate integrals that we're adding. The integral from 0, not from 0, from my starting point, which is pi over 4, starting point for this integral, to pi over 2. And now the difference is sine is on top. So we need to do sine of x minus cosine x dx. And then we're going to integrate this. So I want you to integrate this by hand just to practice with trig values. So I'm going to pause the video and do the same thing, and then you can come back and check it. So if you work out all the math, you integrate cosine and sine, so you get cosine is sine of x, sine is negative sine, so is negative cosine, so you get cosine, upper bound minus lower bound, and then you do the same thing for the other side, and you should get 0.828 if we're accurate to 3 decimal places. So you can pause to look at that more. Then for the next example, it says determine the area of the region bounded by these two curves, and x equals -2 and x equals 5. So the difference is it doesn't just want where they intersect, it wants this whole region. And they already graphed it for you. And as you can see, it's broken up into 3 separate regions. This region where the red curve is on top, this region where the blue curve is on top, and then again the last region, which is from here to here, which is the red. So we have 3 integrals. I'm going to again set them equal to each other to find the points of intersection. I mean, it looks like it's 3 and it looks like it's -1, but we're just going to verify. So I'm going to get everything to one side. I'm going to first factor out a 2 to make it easier to factor. And then I'm going to factor this. So I get x, this is a -3, so I want x minus 3, x plus 1 equals 0 if I set each term equal to 0. Then we're going to get x equals 3 and x equals -1. That's true. So those are our bounds. So we're going to do 3 regions. I'm going to go from -2 to -1, and then upper curve minus lower. So upper is the red, which they're telling me is 2x squared plus 10, minus the lower, which is the line, which is 4x plus 16. Make sure that's in parentheses. And then I'm going to add the integral from negative 1 to 3. Now my line is on top, so I'm going to do 4x plus 16 minus, again, parentheses, 2x squared plus 10. And then I'm going to add my third region, which is from 3 to 5, and then this time the parabola is on top again. And then I'm going to subtract my lower curve. And then again, we can, if you had to do it by hand, you'd combine your like terms and integrate the whole thing. But we can integrate this all on our calculator, and if you would do that, you would get 142 divided by 3. Okay. And if you don't simplify, then just make sure you have your parentheses when you integrate. Okay, so the other type of example, what can happen is they might give you an equation like this. So they want to find the area between x equals 3 plus 2y minus y squared and x plus y equals negative 1. If you have a Casio, you can go to the conics and graph the sideways parabola, but you won't be able to graph the line on the same curve. So that makes it a little bit more difficult. So you probably will need to make a t-table. And when you do your t-table, you will have to plug in y values first. And then plug those in to get your x values. So I just quickly made a t-table before, and these are the values I got, and then I plotted them to help me see what it looked like. And then this one I just solved to negative x minus 1, went down 1, and then a slope of negative 1. So these are my two curves. Now with this, if I drew my rectangles vertically, I would have to do two different curves. And the problem is there's no way to solve this curve, the x equals 3 plus 2y minus y squared for x. And so what we can do in order to make it easier, and when we can't solve for y, is we're going to draw our rectangles horizontally this way. And which means this width now is dy instead of dx. And when that happens, that means everything is in terms of y. So that means my bounds are going to be the y values between them. And when we do our upper curve minus lower, when we're doing that, we're looking at which curve is more positive horizontally, which means the one to the right, because these x values are more positive than these y. So when we do in terms of y, the area is actually going to be the x1 minus x2 when we integrate, and then we're going to have dy. So we're going to do the 1x curve minus the other one. So we're going to actually have to solve for x, and then we have to get everything in terms of y. So like this would be x1, and then if I solve this curve for x, I would get negative 1 minus y. This would be x2. And so the change in height would be this x value, which is x1, minus this x value, which is x2. So that's the change in height. But then because we're integrating with respect to y, we have to substitute my equation for the x value. So in this case, my parabola is more to the right. So I'm going to do 3 plus 2y minus y squared minus, and then I'm going to subtract my other curve, which again I need to have solved for x so I can get it all in terms of y, and I'm going to have negative 1 minus y, and this is dy. And then when I do my bounds have to be my y values. So I need to figure out where these two curves intersect again. So again, I would set, if I come up here and set my two curves equal to each other, so I'm going to solve both for x, and then I'm going to set them equal to each other. And then I'm going to get everything to one side. Factor, so I get y plus 4 sorry, I lost my middle term. My middle term would be 3y. Okay, because I would have negative y minus 2y. So it would be a minus 3y. And then I would have a minus 4 because I do negative 1 minus 3. So then I would get y minus 4 and y plus 1. So y is going to be 4 and y is going to equal negative 1. So those are my bounds from negative 1 to 4 because I want the area between the two curves. So I want where they intersect. Because I'm dy, I'm going to do the y bounds. Now when you integrate this on your calculator, you can't integrate with a y, so you just use x as your variable. I'm going to combine my like terms, so I get 3 minus negative 1, which is 4, minus, or it's going to be a plus, a 2y minus a negative y, so plus 3y minus y squared dy, and then you can integrate that in your calculator again, and we get 125 over 6. So sometimes you might have to draw your lines horizontally, and that means everything is in terms of y. So these are the last two are two old AP questions we're going to quickly do. On the second one, you can only do part A. So for this says, this is my region. It is non-calculator, just so we know. And they said let R be the region in the first quadrant enclosed by the graph of f of x equals 8x cubed and g of x equals sine of pi x. Write an equation for the tangent line of f at x equals 1/2. So I'm going to take my derivative, which is 24x squared. I'm going to find the slope at 1/2 by plugging that into my derivative. And if we do that, we get 24 over 1/4, so my slope is 6, and then I'm going to have y equals 6 times x minus 1/2, and then I need to find f of 1/2, which gives me 8 times 1/2 cubed, which is 8 times 1/8, which is just 1. So I'm going to have plus 1, because my equation of my tangent line again is f prime of a times x minus a plus f of a. Okay. And then part B says find the area of the region. So if I look at this, I can draw my rectangles vertically because everywhere this curve is above this one. I have to identify which one is which, so we should know that this one looks like sine of pi x and the lower curve looks like 8x cubed. And so when I integrate this, I'm going to go from 0. This is nice because they told you where they intersected by this point. So I'm going to go from 0 to 1/2 of the upper curve, which is sine of pi x minus 8x cubed dx. And then pause the video and integrate this by hand and then come back and check it. So this is what I would get when I integrated. Don't forget to divide by the derivative of the inside, which is pi, and you can actually stop at this step. And that's perfectly acceptable answer. So you didn't have to figure this out, and because I don't have a calculator, I would have 1 over pi minus 1/8. I can't figure out what that is because I don't have a calculator. And then the last one, we're only going to do A for now. The next few days we're going to learn B and C. But it says, again, no calculator. It says let R be the region in the first quadrant, bounded by the graph to the square root of x, which is this bottom curve, and the horizontal line y equals 6, and the y-axis, find the area. So for part A, we're going to integrate. Again, we can draw our rectangles vertically because no matter anywhere in this region, the y equals 6 is above the y equals 2 minus square root of x. We would do 6 minus the lower curve, which is 2 the square root of x. We would integrate from 0 to 9 dx, and we use the x bounds because we're in terms of x. And then again, you would integrate this, so I'd get 6x minus 2x, it's to the 1/2, so it becomes to the 3/2 divided by 3/2 from 0 to 9. And then if I come down here, I just have to, when we don't have to simplify, we do have to plug in the bounds. So if I multiply by the reciprocal of 3/2, I get 4/3 times 9 to the 3/2, and then minus, and then this term would just be 0, so you can put that, and then I'm just going to leave it like this, but you could simplify, but that would be my answer. And the next few days we'll learn how to do B and C. Okay, so that is your lesson on area between two curves.